All right, let's talk about 6.24 and 6.25 from the end of chapter questions. This is a sort of a conceptual problem. It asks you to draw enthalpy diagrams for either an exothermic process, I believe that's 624, or an endothermic process, that's 625. So an exothermic process is when a reaction occurs or else some physical process occurs that essentially releases heat to surroundings, okay? And that's how it's defined, basically, okay? It's going to have a negative delta H that's associated with it, or an enthalpy change, negative enthalpy change. Now, on the other hand, the opposite process is the endothermic, okay? In the endothermic process, heat is absorbed into the system from the surroundings. Think about a case maybe where you have a beaker and there's a reaction that takes place in that beaker, and you feel the beaker, it's getting very cold as the reaction's occurring. This is not because that reaction is, heat's disappearing. What's happening is the reaction requires an input of heat energy to go, to react. And that can only come from the surroundings. So when you touch that beaker and it feels cold to your touch, the reason why is because that system, the reaction system, is absorbing heat essentially from your hands, which makes up the surrounding. That heat loss makes it feel cold. Okay, so this is an endothermic reaction. Exothermic reaction is the opposite. That's where heat's released to the surroundings. That's like combustion reactions, or exothermic, usually highly exothermic. In the case of the endothermic, they're going to have a positive delta H, or a positive enthalpy change that's associated with it, okay? Now, what else about these guys? Well, oftentimes chemists like to show the progress of reactions by enthalpy diagrams, or sometimes they're called reaction coordinates. Your book shows these a little bit differently than what I am used to. So I'm going to explain both ways to show the same thing, essentially, okay? So what this enthalpy level diagram is there's an imaginary y-axis, okay? And that y-axis is an enthalpy axis, or H. H is our symbol for enthalpy, capital H, okay? And this is how your book does it, okay? There's two lines or locations or addresses, if you want to think of it that way, on this enthalpy diagram, and they're shown by these two horizontal lines, okay? Now, the horizontal lines basically represent reactants or products for a reaction, according to the way your book does this. So let's just say A reacts to form B, some hypothetical reaction, okay? Some kind of hypothetical reaction. So if we have a situation where A is down here, and, this is exothermic, where A is up here, and B is down here, and the progress of a reaction is denoted by an arrow. And oftentimes in your book, this arrow might be filled in, okay? It's like a big block arrow, basically, okay? But the arrow goes from the top, this line, down to B. Okay, this is a situation where the enthalpy originally was higher than the final enthalpy. So the final is a little bit lower. So if I did, remember, if you ever calculate delta something, right? Here, delta H, you always do what? Final minus initial. Alright? So final minus initial, if I did that numerically, I will get a negative value for this. Okay? So that then is characteristic with an exothermic diagram. If you go from high to low, as a result of chemical change, that's exothermic. Now, conversely, how would your book show an endothermic? Well, the diagram would look pretty similar for an endothermic case, okay? There's still this y-axis, which is my enthalpy, or H, okay? Hadn't changed. I still have two horizontal lines representing reactants and products. It's just that the difference here, things might change around a little bit, okay? Things might change around a little bit. So for instance, we might go from a spot of low enthalpy to higher enthalpy with our arrow. So now we're kind of going up. As A reacts to make B, we're at a higher enthalpy. So this enthalpy gap between where we start and where we finish, it has to be bridged somehow, right? We have to get from point A to point B, literally in this case, right? It's kind of funny. But nonetheless, we have to bridge that gap, that enthalpy gap. And that can only be done if heat energy is absorbed from the surroundings. The surroundings provide heat into the chemical system to make A react to form B. That is an endothermic process. Now, while we're on this, okay, while we're on this subject, for a process which is endothermic, such as this reaction, A making B, where we go from a lower enthalpy to a higher enthalpy, would I want to show my heat energy as a reactant or a product in a balanced chemical equation? Doesn't it make sense that I'd write it right here as a reactant? I would take substance A and I would add energy in the form of heat to bridge that enthalpy gap to make product B. For endothermic reactions, heat is a reactant. You can treat it that way, right? Now what about the opposite case? Remember our exothermic reaction, A to B, where we went from the higher and we went down to the lower enthalpy? That's our exothermic case, right? Would I list my heat energy given off as a product or a reactant? Here, it'll be a product, of course. This is like combustion reactions. In this case, exothermic reactions, heat energy is given off to the surroundings. It feels hot to the touch, right? Think about combustion reactions. So we can list heat energy as either a reactant for the endothermic case or a product as the exothermic case. This is another thing that we want to learn how to do. Okay, now lastly, I want to talk about a slightly different diagram for endo and exothermic reactions. It's more or less the same. It's just the appearance is a little bit different from what your book likes to do. The way it's presented in your book is a little bit different to me. Oftentimes I see these diagrams represented slightly different graphically. Now this y-axis actually will be the same, okay? It's just going to be the enthalpy or the H. But the x-axis is something that's a little bit different, okay? I like to call that the reaction progress axis. Okay, let's still consider a reaction A being converted to B, whatever that is. Okay? So let's just say that we start off right here with reactants A. And that line still represents the magnitude or the value for the enthalpy of reacting substance A, whatever that is. Okay? And then over here somewhere on the right, and this is kind of a non-quantitative, the reaction progress is a non-quantitative or semi-quantitative axis, I guess you could say, okay? Because over here on the far right, we've got our products, B. So what I mean by reaction progress, it's almost like over on the left is the start of the reaction, and then over on the right is the finished, the end of the reaction, when it's finished, right? So somehow we get from point A to point B, right? And typically that involves going through a little hump and then coming down and settling here at point B. This little hump is actually going to be really important later on for you in chemistry, because that's going to be called the activation energy of the reaction, or it's going to be related to that activation energy. That controls how fast this process can occur. But for right now, we don't have to worry about that too much, because what I really want to worry about the most is the net difference between point B and point A. That is our delta H, or our change in enthalpy, final minus initial, right? Final minus initial. Now, in this case, what sign would that delta H, that change in enthalpy, accompany? Would it be positive or would it be negative, do you think? Final minus initial. To me, it appears as if this change would be positive, because B is higher than A. There's been a net input in heat energy. So as I have this written right here, let me erase this so there's no confusion, okay? As I have this written right here, this is an endothermic reaction coordinate. Right? So it's pretty similar to the way your book described it. It's just that there's a fixed starting point, there's an end point, and you get from one point to the other, and then basically which line is higher is going to tell you whether it's endothermic or exothermic. But this one's going to be endothermic. Now, if that's the case, then let's think about what the opposite case would look like, the exothermic. So we'll still consider A to B. Now let's think exothermic. This is the one where the heat's given off, okay? I'm still going to have a line on my left that shows my reactants, essentially. Still going to have a line on the right which shows my products. I'll call that B here. Still going to have some kind of hump that I got to go through. Okay. That's my EA, or my activation energy. This one's smaller than the previous case, so actually this reaction will be expected to proceed a little bit faster than the previous case, most likely. But again, I don't care too much about that, but the magnitude of that is important for the speed of reactions, or the rates of reactions. You'll learn more about that later. What I care about right now is this difference, because that's my delta H, my enthalpy change for this process. Now, what's different about this figure from the one we considered earlier is this line is below this line on my reaction coordinate. So if I do final minus initial, I'm subtracting a bigger number. So my change will be negative. And as a result, this is an exothermic process. This is the one where heat energy is given off to the surroundings, and the system starts feeling warm or hot to the touch. Okay? Exothermic. Alright, so I hope that this was helpful. You're going to need to understand how to interpret these diagrams. On a test, I mean, it's multiple choice, so you're not going to be asked to draw one, most likely. But it's really easy to give you a picture of one, ask whether it's endothermic or exothermic. Ask you lots of different things about the reaction based upon your interpretation of these diagrams. So that's why it's important to pick this up.